Close your eyes and envision the sheer, staggering absurdity of trying to power a massive, multi-million-dollar silicon supercomputer using nothing more than the meager chemical energy stored inside a single, ordinary potato. This image is immediately ridiculous because a potato, with its tiny chemical potential, could barely flicker a dim light bulb, let alone drive the trillions of floating-point operations required for modern artificial intelligence. Yet, the biological organ sitting silently inside your skull weighs roughly the same as a small bag of potatoes, and consistently outperforms the world's most advanced silicon architectures in adaptability and learning. This biological masterpiece, composed of living tissue and electrochemical signals, operates on roughly 20 watts of metabolic power, the same caloric equivalent as a very light lunch. In a world defined by energy-hungry data centers, a single complex query to a modern large language model can consume up to 6,000 joules of energy, highlighting an immense efficiency gap. Today, we are embarking on a deep technical journey to explore why the human brain remains the ultimate, self-assembling, self-optimizing, and self-repairing biological large language model ever conceived. We will navigate the intricate landscapes of wetware to understand why modern silicon hardware is still desperately playing catch-up with the elegant, frugal efficiency of our own living neural networks. At a high level, both your biological brain and artificial models like GPT-4 are vast, distributed systems engineered specifically for the monumental task of hierarchical pattern recognition. This fundamental principle of building complexity from simplicity forms the core of our comparison. Though the actual underlying mechanisms and the substrates they inhabit differ in profound and unexpected ways, your brain accomplishes its incredible cognitive feats through a dense, living network of approximately 86 billion neurons that are perpetually communicating via rapid, asynchronous electrochemical pulses. Modern large language models, in contrast, must deploy their parallel computations across thousands of high-power hardware accelerators and specialized silicon chips to achieve anything even remotely resembling human-level function. At the core of both systems lies the sophisticated principle of hierarchical abstraction, where simple, raw sensory inputs are progressively refined into increasingly complex and meaningful internal representations of the world. Within your visual system, simple neurons respond to basic features like edges and orientations before those signals are combined into recognizable shapes, 3D objects, and eventually entire narrative scenes. This sophisticated layered processing architecture allows your mind to construct incredibly complex cognitive models from nothing more than the elementary sensory data hitting your eyes and ears every single second. Transformer-based LLMs operate in a strikingly similar fashion, employing a multi-layered digital architecture where each successive layer further refines the semantic representation of the input text it receives. Through a series of complex attention heads and feed-forward networks, these models capture relationships across different levels of granularity, ranging from individual characters to entire semantic arguments. This remarkable commonality in building complexity from simplicity explains why researchers have found significant alignment between LLM activity patterns and the actual activity in human language brain regions. However, a major architectural divide exists because the brain's parallelism is fundamentally analog and event-driven, whereas an LLM's parallel processing is strictly digital and dictated by a rhythmic hardware clock. Your brain is also inherently resilient to physical damage. The loss of a small portion of the network rarely causes total functional failure because your neural pathways are built with overlapping redundancy. LLMs demonstrate a different kind of fault tolerance through their statistical nature, where the collective output of many interconnected nodes tends to produce coherent results, even if individual calculations are imperfect. The most critical divide between these two systems lies in the actual source and nature of the patterns they are designed to recognize and process for the purpose of intelligence. Your cognitive patterns are derived from direct embodied interaction with the physical world and are shaped by the unrelenting pressures of evolution, homeostatic needs, and survival. This means your cognition is deeply intertwined with your bodily states, your emotions, and your consciousness, emerging from the integrated dynamics of volition and real-world awareness. In contrast, the patterns learned by LLMs are purely statistical artifacts extracted from massive, disembodied corpora of text that have been scraped from the vast and often noisy corners of the internet. This is why an LLM can describe the complex physics of walking with perfect linguistic accuracy without ever having experienced the physical pull of gravity or the sensation of movement. The AI has absolutely no experiential knowledge of balance, muscle tension, or the weight of its own existence, as its entire world is composed of tokens and digital correlations. The brain's patterns are real-world, physical phenomena rooted in biology, while an LLM's patterns are merely statistical correlations living within the cold, abstract vacuum of a digital medium. This leads us directly to the revolutionary concept of neuroplasticity, which is the brain's remarkable ability to physically change its own structure and connections in response to every new experience. There is a famous saying in neuroscience that neurons that fire together, wire together, creating a lifelong journey of structural adaptation and the constant refinement of your internal world. We must view the human brain as a complex adaptive system that exists in a perpetual state of flux, constantly self-organizing to meet the demands of its changing environment. It uses local measures of neuron activity to trigger the physical growth or pruning of connections, allowing the system to adaptively reshape its own hardware infrastructure on the fly. This ongoing process is what enables you to learn new skills, recover from brain injuries, and adapt to entirely new environments without ever needing a costly or time-consuming factory reset. But in sharp contrast, a large language model is essentially a static computational graph that becomes frozen in time once it's intensive. Month-long training phase has finally been completed. Its knowledge is encoded in a vast set of numerical weights that remain fixed during the inference process, meaning it cannot truly learn from you during a single conversation. While techniques like fine-tuning allow an LLM to adapt to new domains, this process is fundamentally different from the fluid, organic plasticity found in a living, breathing biological brain. Fine-tuning often requires a computationally expensive retraining cycle on massive new datasets, which may not even alter the model's underlying architectural foundations in any meaningful or permanent way. This structural rigidity can lead to a phenomenon called catastrophic forgetting, where the model unexpectedly loses its previously acquired knowledge while it is trying to learn something entirely new. The human brain, however, manages to integrate action, emotion, consciousness for a holistic, context-aware understanding of the world that no current silicon software can truly replicate. We also possess the gift of metacognitive monitoring, which allows us to evaluate our own confidence in a decision and strategically adjust our behavior when we feel we are uncertain. LLMs operate as disembodied predictors of text, lacking any genuine sense of self, internal belief states, or the intentionality required to understand the goals they are helping us achieve. Now, let us talk about the physical substance of these two systems, the fundamental difference between the biological wetware of our minds and the industrial silicon of our machines. Neurons are the primary building blocks of this wetware. Each one, a living cell with dendrites to receive signals and an axon to transmit output via complex synapses. But neurons don't work alone. They are supported by glial cells like astrocytes, which provide metabolic support and modulate the strength of your synaptic connections. Oligodendrocytes produce myelin, the insulating sheath that allows for rapid signal transmission across the brain, ensuring your thoughts move with the speed and efficiency required for survival. Even the brain's immune cells, known as microglia, play a role in intelligence by selectively pruning away weak or unused synapses to keep your neural network lean and efficient. Communication in this biological network is not just electrical. It is a rich chemical language involving neurotransmitters like glutamate for excitation and GABA for essential inhibitory balance. Neuromodulators such as dopamine and serotonin act like a global volume control, gating synaptic plasticity based on reward, attention, or your current emotional state. This biological complexity provides a blueprint for computation that is currently orders of magnitude more efficient than even the most powerful artificial systems ever built by human hands. To put this in perspective, generating a single paragraph of text from an LLM can require roughly the same amount of energy that a human being uses over several days of thought. The massive training phase for a model like GPT-3 consumed an estimated 187 megawatts of electricity, enough to power hundreds of suburban homes for an entire year. Biological wetware operates on relatively slow analog electrochemical signals known as spikes, which allow the brain to perform massive computations without burning through its precious fuel. Because energy is only expended when a neuron actually fires a spike, the brain is an inherently frugal, event-driven system that prioritizes metabolic efficiency above all else. Silicon hardware, however, relies on the incredibly rapid switching of billions of transistors, a digital process that generates massive amounts of heat and requires a constant high-voltage power supply. This intense heat production requires the construction of colossal cooling infrastructures and data centers, which significantly increases the carbon footprint and environmental impact of modern artificial intelligence. Beyond just raw power usage, modern AI faces a hidden structural wall known as the memory bandwidth bottleneck that severely limits how fast information can actually move through the system. Our current computer systems spend the vast majority of their time and energy simply moving data from slow off-chip memory into the fast processing units where calculations happen. In your biological wetware, memory and processing are never separate entities. Instead, they are beautifully co-located within the physical synaptic connections themselves. This integrated architectural design completely eliminates the need for costly and energy-hungry data shuttling, which is the primary secret behind the brain's superior computational efficiency. It represents a fundamental departure from the traditional von Neumann architecture that has underpinned nearly all modern computing and AI hardware for the last 70 years. Scaling up LLMs today requires exponential increases in physical computational resources, leading to prohibitive economic costs and growing logistical challenges for the world's tech giants. Your brain scales its power through metabolic energy and nutrient intake, growing and adapting within the sustainable constraints of its biology without needing to build a massive power grid. Looking toward the future, speculative technologies like wetware as a service could eventually bridge this gap by connecting lab-grown brain tissue directly to our digital cloud interfaces. Imagine a world where you could rent remote access to lab-grown brain organoids to perform highly complex nonlinear tasks that traditional silicon chips simply cannot handle efficiently. These hybrid systems would leverage the innate efficiency of biological tissue, managed through the familiar technological frameworks we already use to run our software today. This bold convergence of hardware, software, and living wetware represents the next great frontier in our quest to understand and replicate true general intelligence. While both systems exhibit powerful pattern recognition, we must remember that their intelligence is born from two fundamentally different places and serves two different masters. Human intelligence is an adaptive instrument, designed primarily for survival, while LLM intelligence is an emergent property, born from the statistical analysis of vast datasets. We learn through implicit, exploratory interaction with a changing environment, building a holistic and context-aware understanding of what it means to actually exist in the world. LLMs rely on a batch training paradigm on static datasets, which makes them surprisingly brittle and prone to failure when they encounter a situation they have unseen before. This leads to a significant robustness gap where humans can handle ambiguity and noisy information with ease, while AI often starts hallucinating or fails entirely. LLMs are notoriously sensitive to the exact phrasing of a prompt and can be easily derailed by minor perturbations or unexpected changes in their digital input data. Emerging research in the field of Neuroai is now seeking to bridge these fundamental differences by building new AI architectures, inspired directly by biological principles. One of the most promising brain-inspired architectures is the spiking neural network, which mimics the brain's event-driven and low-power method of communication using timed pulses. These systems use discrete timed pulses called spikes instead of continuous digital values, allowing for high-efficiency computation that could eventually revolutionize robotics and edge computing. Another revolutionary concept is predictive coding, a theory suggesting the brain is an active predictor that focuses its energy solely on processing unexpected prediction errors. This approach is inherently efficient because computation is concentrated only on the unexpected events, rather than recalculating every single thing the system already knows to be true. By focusing only on what is surprising or new, the brain maintains a highly accurate and energy-efficient generative model of the entire physical world around it. Neuromorphic computing aims to design physical hardware that emulates this exact biological structure, finally moving us away from the limitations of the traditional computer chip. We are rapidly moving away from the era of brute force, scaling, and toward a new era of biologically plausible learning that prioritizes quality and efficiency over sheer model size. The ultimate goal is not merely to build a bigger or faster LLM, but to architect a new class of machines that truly approximate human-like cognition and robustness. However, as we move closer to this synthesis of man and machine, we must address the urgent and complex ethical concerns that this convergence inevitably raises. Access to sensitive neural data through advanced neurotechnology and brain-computer interfaces raises profound questions about our personal privacy, our fundamental cognitive liberty. New technologies that have the power to alter brain function or integrate with our neural circuits will challenge our long-held notions of agency, autonomy, and personal identity. The prospect of creating sentient or conscious wetware in a lab forces us to redefine what moral status means and what rights these new biological entities might deserve. These are not just technical hurdles for engineers to solve. They're fundamental existential questions that will define the future of our species and our global society. The future of artificial intelligence does not lie in more silicon alone, but in the creative fusion of biological insight and our most advanced technological innovations. We are finally learning that energy efficiency and structural plasticity are not just optional features, but are the very foundations of true embodied intelligence. The long journey from silicon back to wetware is only just beginning, and it promises to fundamentally transform how we interact with the technology in our daily lives. By embracing the complexity and the ancient wisdom of the human brain's architecture, we can unlock entirely new realms of computational possibility that were once thought impossible. A single potato may never actually power a supercomputer, but your own brain, fueled by that same meager energy, remains the most sophisticated infrastructure in the universe. If you found this deep dive into the concept of the biological LLM fascinating, please help our own channel's algorithm grow by hitting the like and subscribe buttons. Thank you so much for watching, and as always, stay curious about the incredible biological wetware that is working inside your head right now. But answer me this: if we can eventually rent out your extra neural processing power like a cloud server, would you trust an AI to borrow your neurons while you sleep?